I want you to picture a scenario that almost everyone has lived through at some point.
Oh, I'm sure I have.
Right. So you are rushing down a busy street, you're balancing a coffee, taking a phone call, and you frantically scribble a quick note on the back of a receipt.
Like a gate number or something.
Exactly. A gate number or maybe a client's address. And then a few days go by.
Right.
You pull that crumpled paper out of your pocket, you completely misread your own frantic handwriting, and you end up making a totally wrong decision based on it.
You show up at Terminal 3 instead of Terminal 2.
Yes. Or you call the wrong vendor entirely. You essentially create this, like, false reality for yourself based on a really bad note.
It is a uniquely frustrating failure of personal data management, honestly.
It really is.
Because you rely on that external memory, and you just assume it is perfectly accurate because, well, you wrote it yourself.
Right.
And then you execute an action that turns out to be entirely misguided.
So take that very human mistake, that little moment of self-sabotage, and apply it to the autonomous AI systems we are building today.
Oh, wow. Yeah.
Imagine an AI agent doing that same exact thing, but, 1,000 times faster, across massive data sets, and making complex, compounding decisions based on a misread scribble.
That is a terrifying thought.
It is. And today, we are unpacking a fascinating new state-of-the-art paper from researchers at Florida State University.
That's right.
They have introduced a concept called ConsistencyGate, which is basically a pipeline architecture designed specifically to stop LLM agents from giving themselves false memories.
Right. And to appreciate what ConsistencyGate really does, we first have to draw a hard line between standard chat models and the long-horizon LLM agents that this paper focuses on.
Yeah, that's an important distinction.
It is, because when you use a standard web-based chatbot, it is effectively stateless.
You close the tab and it's gone.
Exactly. The context window is wiped, and it completely forgets you existed. But long-horizon agents, the kind deployed to manage software projects or monitor customer service pipelines.
Or act as personal assistants over months.
Right. They cannot operate that way. They have to maintain an external memory store, which is usually a vector database.
Okay.
So as they parse documents or interact with you, they continuously extract atomic facts. They write them down to this database, and then they use a retrieval-augmented generation loop to recall those facts later to solve multi-step problems.
Okay, let's unpack this. Because in theory, that architecture is incredibly powerful, right?
Oh, absolutely.
You have an agent that builds a persistent, evolving context of its environment. But the researchers point out a massive, catastrophic vulnerability here.
Yeah, the hallucination problem.
Right. We all know LLMs hallucinate. So if the agent's extraction module hallucinates a fact, like if it misreads the environment and writes a falsehood into its own vector database,
then that hallucination stops being a temporary statistical glitch.
exactly. It becomes a permanent structural false premise that the agent will just treat as absolute truth going forward.
And the paper isolates this specific failure mode, dubbing it memory contamination.
Memory contamination.
Right. The extraction process is basically where the poison enters the well. And the source text gives this really highly illustrative example for this.
Okay, lay it on me.
So imagine you feed the agent a really simple contextual block. Like Alice is 34. She works at TechCorp. She has 2 kids.
Okay, simple enough.
The agent parses this to extract atomic facts for its long-term storage. And it successfully writes down Alice is 34 and Alice works at TechCorp.
But because LLMs are, ultimately probabilistic engines sampling from distributions, the temperature or just the statistical noise might lead it to output something slightly off.
Right.
Like it might say Alice has 3 kids, or it might hallucinate an adjacent detail entirely and generate Alice graduated in 2012.
Yes. And what's fascinating here is the downstream effect of that single probabilistic error.
Because it doesn't just stop there.
No, it doesn't just result in one wrong answer later on. The paper details how this creates a contamination cascade.
A contamination cascade. That sounds bad.
It is, because the agent relies on this database for all its future reasoning, right?
Huh?
So a single right-time error compounds over a long interaction trajectory.
So it pulls that false fact into its working memory.
Exactly. It uses it to deduce new assumptions, and then it writes those new flawed deductions back into the database.
Wow.
Yeah. The researchers actually mapped this behavior and found that by turn 90 of a continuous conversation, an unchecked memory store becomes completely overwhelmed.
By turn 90.
Yes. The false premises just actively crowd out the factual ones.
Yeah, I look at this like a compounding navigation error in a ship's guidance system.
That's a great way to look at it.
Right, like if your initial sensor reading is off by just a fraction of a degree on day 1, you don't just miss your port.
Right.
By day 10, you were sailing on the wrong side of the continent. Every subsequent calculation is referencing a corrupted baseline.
Exactly.
But, and here's where I have to push back a little on the premise of the problem.
Okay, go ahead.
We have highly sophisticated database management systems today, right? If an AI writes down a bad memory, why can't the overarching architecture just run a cleanup protocol later?
Like a sweep.
Yeah. Why doesn't the system just evaluate the database and prune the bad nodes when it realizes they are useless or when it runs out of space?
That logical leap right there, that highlights the exact blind spot the researchers identified in current AI memory management.
Oh, really?
Yeah. Existing frameworks are structurally blind to truth because they are optimizing for entirely different metrics.
Like what?
Retrieval and capacity.
Okay.
So retrieval mechanisms, like cosine similarity searches in vector spaces, they're merely looking for semantic proximity.
Meaning they just want things that look related to the question.
Exactly. If you ask the agent about Alice's education, the search algorithm will flawlessly retrieve the hallucination Alice graduated in 2012.
Because it perfectly matches the semantic shape of the query.
Yes. A flawless retrieval system fetching a hallucination just delivers a lie faster.
So it's optimizing for relevance, completely divorced from factual accuracy.
Right.
If the hallucination matches the query vector, the system just assumes it's a high-quality node.
Exactly the issue.
Yeah.
And when we look at the other metric, which is capacity management, the problem just compounds.
Because you have to delete stuff eventually.
Right. When a vector database approaches its storage limit, the system employs utility filters to decide what to evict and what to keep.
Okay, and how do they decide?
These filters typically rank memories based on recency, novelty, or topical relevance.
Oh, I see where this is going, which creates a massive vulnerability because a hallucinated fact, like Alice lives in New York, scores incredibly high on all those utility metrics.
Yep.
It's a highly relevant, entirely novel, and recently generated piece of data.
It's the illusion of utility. A utility-based admission policy looks at that hallucinated fact and prioritizes it over older true facts.
Wow, so the hallucination just walks right past the filters.
Yeah, because a mathematically hallucinated string looks structurally identical to a factual string in a vector database.
So managing the archive after the fact is just a lost cause.
Pretty much.
The system is just sorting and organizing the hallucinations more efficiently at that point.
Exactly. And if we connect this to the bigger picture, this is about shifting from managing an AI's archives to basically putting a bouncer at the door of the archive room.
Okay, I like that analogy.
Okay.
So the core insight of this paper then is that you have to shift the intervention point.
Right.
You can't filter the database. You have to evaluate the correctness of the fact at the exact millisecond it is extracted before the right operation is ever committed to memory.
Yes. And this brings us to the architectural solution the researchers designed, which is ConsistencyGate.
The bouncer.
The bouncer. It relies on an automated self-consistency protocol they call K-sample verification.
Okay, how does that work?
So when the agent's extraction module proposes a candidate fact, the gate intercepts it. It basically pauses the write stream, takes the candidate fact alongside the original source context, and queries the LLM to verify the entailment.
It asks the model to double-check its work.
Exactly. And crucially, it queries the model K times. The optimal configuration established by the researchers sets K to 5.
Got it. So by querying it 5 separate times, we are forcing the statistical engine to prove its own work across multiple inference paths.
Right.
But how is the model actually evaluating it? I mean, we aren't just asking for a thumbs up or thumbs down.
No. We are asking for a nuanced evaluation using soft scoring.
Soft scoring.
Yeah. The verification prompt forces the AI to rate how strongly the source context supports the candidate fact on a continuous float scale from 0 to 1.
Okay.
So a score of 0 indicates direct contradiction. A 0.5 suggests ambiguity. Perhaps the fact is adjacent to the text but not strictly provable.
And a 1 would be explicit, undeniable textual support.
Exactly.
So because we run this K = 5 times, we generate an average score across the 5 samples.
Right.
And this is where the system introduces the threshold, which they denote as tau, right?
Yes, the tau threshold.
And the researchers found that setting a rigid tau of 0.7 operates as the optimal bouncer.
It does.
So if the 5-sample average hits 0.72, the memory is committed to the database. But if it averages, say, a 0.3, The right operation is completely ousted and the fact is discarded.
Exactly. For instance, if the candidate fact is Gina said painting feels like magic, but the raw context actually discussed Gina finding dancing magical, the verification loops will consistently score to 0.
Which prevents the contamination entirely.
Right, and the paper introduces a highly elegant fallback feature for this threshold called an adaptive schedule.
Okay.
This is designed for systems where developers cannot manually tune a static tau value. The threshold tau basically scales dynamically based on the remaining capacity of the memory store.
Here's where it gets really interesting to me, because it mimics an operating system managing cache resources.
Yes, it really does.
When the agent is first deployed and the vector database is virtually empty, the tau threshold is lower and more permissive.
Right.
It might allow facts scoring a 0.5 or 0.6 through, just ensuring the agent quickly builds a functional context window to work with.
Because it needs some data to function.
Exactly. But as the storage capacity dwindles, the algorithm tightens the bottleneck. The bouncer becomes increasingly strict, demanding closer to a perfect 1.0 score before allowing any new fact to consume that premium remaining database space.
It's a brilliant resource allocation strategy, honestly.
It is.
However, relying on this 5-sample soft scoring architecture introduces a pretty severe operational bottleneck.
The latency.
Yes.
Let's be real. Think about a real-world deployment here.
Yeah.
If an AI assistant is listening to a live 1-hour meeting and attempting to extract dozens of action items and facts,
Pausing to query the LLM 5 separate times for every single extraction is going to crush the system.
you are introducing massive blocking latency to the pipeline.
You are. And the empirical data actually supports your concern here. The researchers measured the latency of the 5-sample soft scoring, and depending on the model size, it takes between 264 to 363 milliseconds to verify a single fact.
Oh, wow. Over a third of a second per fact.
Yeah. In a high-throughput data pipeline, stacking hundreds of those 300 millisecond pauses results in unacceptable dead air. The agent just falls hopelessly behind real-time execution.
But how do they fix that?
Well, to circumvent that, the paper outlines a highly technical single-pass alternative designed specifically for latency-sensitive applications.
Okay.
Instead of running the full generative soft scoring loops, they utilize token-level log probabilities.
Log probabilities. Okay, let's look at the mechanics of this. Usually generating text is slow because the model is autoregressive, right?
Right.
It calculates the probabilities for the next word, samples one, appends it to the sequence, and runs the entire calculation again for the next word. It's a sequential, time-consuming loop.
Exactly. And the log prob shortcut bypasses that generation loop entirely. The gate formats the verification as a strict binary prompt. It asks, is this fact supported by the context? Answer only yes or no.
Oh, okay.
But instead of actually waiting for the model to auto-regressively generate the word yes or no, the system just halts at the final layer and inspects the raw, unnormalized logits.
The logic.
Yeah, the internal probability distribution for the very first token.
I see. So we just look at the mathematical weight the model assigned to the yes token versus the no token before it ever actually speaks.
Exactly.
And because we only require one single forward pass through the neural network to read that internal state, we strip out all that generative overhead.
And the efficiency gains are massive. By inspecting the log probabilities, the verification time drops from over 300 milliseconds down to a mere 23 to 28 milliseconds.
Wow.
Yeah. That represents a 12 to 14 times speed up per fact.
That's crazy.
It allows the gate to operate efficiently in real-time pipelines.
So a 25 millisecond check is essentially invisible to the user. So why wouldn't developers just permanently default to this log prob method? I mean, why ever use the slow 5-sample soft scoring?
That raises a really important question about the nature of the data we process, actually. It leads to a phenomenon the paper terms the bimodality of yes-no support.
Bimodality, okay.
The log prop shortcut is exceptionally reliable, but only when operating on clean, highly structured data domains.
Like database outputs or API logs?
Or technical manuals, exactly. In those environments, the textual entailment is very literal.
Right.
So when evaluating a technical manual, the model's internal probability distribution becomes fiercely bimodal. It places 99% of the probability mass on yes or 99% on no.
The signal-to-noise ratio is just pristine.
Yes.
Because structured data doesn't use subtext. A server log saying error 404 at 10:00 a.m. leaves zero room for interpretation.
Exact.
But when you shift the context to open-ended human dialogue, that bimodal assumption completely shatters, doesn't it?
It does.
Because human conversation is messy.
Very messy.
It's full of fragmented sentences, sarcasm, implicit agreements, and trailing thoughts.
Right. And when you force a binary log prob evaluation on that kind of messy data, the probability distribution flattens out.
Correct.
The model isn't 99% sure anymore. The probability mass kind of hovers around 55% for yes and 45% for no.
So it's basically guessing at that point.
Yeah. And when the distribution flattens, the binary log prob gate becomes super unreliable, generating unacceptable rates of false positives and false negatives.
I see.
Therefore, if the agent is processing unstructured human interaction, developers are basically forced to absorb the latency hit and utilize the slower 5-sample soft scoring to accurately gauge that muddy textual support.
That makes total sense. So that theoretical framework is great, but how does ConsistencyGate actually perform when tested against the frontier models currently driving the industry?
Well, they had to do some work to figure that out.
Right, because the researchers couldn't just use standard benchmarks, right? Surprisingly, existing AI memory datasets completely lacked gold standard labels for fact-level accuracy.
Which is wild when you think about it.
It is, so they had to engineer their own testing grounds.
They did. They constructed 3 distinct data sets to really stress test the gate across different levels of data entropy.
Okay, what were they?
First, they built MemContam, which is a purely synthetic, highly structured data set utilizing biographies and spacecraft operational logs.
Spacecraft logs?
Yeah. This environment was designed to establish the upper performance bounds of ConsistencyGate under ideal, unambiguous conditions.
And then what?
Next, they moved to LocomoContam, which introduced the chaos of the real world.
Okay.
This dataset utilized long-term dyadic conversations, so 2 humans speaking back and forth over extended periods, and they planted specific false facts artificially into the text to see if the extraction gate would catch them.
Ah, clever.
And finally, they built MSC-Contam, which focused on multi-session chats, heavily grounded in shifting personal personas, tracking evolving hobbies and occupations across distinct sessions.
Okay, so a really solid mix of structured and messy data.
Definitely.
What were the results?
The empirical results across these benchmarks firmly validate the architecture.
That's great.
Looking at the highly structured MemContam dataset, they ran the tests using Quinn 2.532b, which is a highly capable open-weight model.
Right.
And without ConsistencyGate active, the baseline memory contamination rate was 50%.
Wow.
Half of the agent's database was populated with statistical hallucinations.
That's essentially flipping a coin on whether its memory of a spacecraft log is real or total invented.
Exactly. But when they activated ConsistencyGate, that 50% contamination rate plummeted to a near Oracle level of 1.2%.
1.2%?
Yeah, it achieved a 97.6% relative reduction in database errors.
That is incredible.
And consequently, with a near-perfect vector store, the agent's downstream ability to reason and execute tasks based on that memory improved dramatically.
Okay, that is a staggering cleanup rate for structured data. But, as we established earlier, the dyadic human conversations in LocomoContam present a much harder entailment challenge, right?
They do?
The bouncer has a much tougher time reading the ID cards, so to speak.
Yeah. On the human conversation dataset, the contamination rate dropped from the baseline 50% down to 34.1%.
Okay, so it's a significant improvement, but it shows that messy data still bleeds through the threshold.
It does. But what is particularly noteworthy about these results is the architecture's agnosticism.
What do you mean?
Well, they didn't just test this on the Quinn architecture. They routed the gate through Jenna, Llama 4 Scout, and the parameter-dense Llama 3.370b.
Okay.
And every single model exhibited substantial reductions in memory contamination.
Oh, nice.
Because ConsistencyGate is a pipeline intervention operating at the extraction layer, it doesn't actually require modifying the underlying model weights.
You can theoretically bolt this gate onto any LLM infrastructure deployed today.
Exactly.
But, and we have to talk about this, implementing this strict extraction gate comes with a pretty severe operational trade-off, doesn't it?
It really does.
We have to look closely at the cost of this strictness, specifically the rate of false negatives.
Right.
When you demand literal, provable textual entailment before committing a fact to memory, the gate struggles profoundly with implicit data.
And this is the most critical limitation identified in the research. Let's look at a specific test case from their logs.
Okay.
Imagine a multi-turn conversation where a user speaks enthusiastically about sourcing clay, struggling to center material on a wheel, and managing the heat of a kiln.
Okay.
The agent's extraction module correctly synthesizes the atomic fact. Melanie is into pottery.
which logically is 100% accurate extraction based on the context provided. Any human would deduce that fact instantly.
Exactly. But when the candidate fact is passed to the verification gate, the gate searches the source context for explicit support. And the word pottery is never actually uttered in the transcript.
Oh, wow.
Yeah, because the gate is optimizing for strict text entailment to hit that 0.7 threshold. It scores the extraction poorly.
So the bouncer rejects a ground truth fact simply because it was deduced rather than explicitly stated?
Yes. In the Locomo Real Conversation dataset, that hypervigilance caused the gate to reject 42% of actual correct facts.
42%. You are sacrificing almost half of the user's factual context.
Yeah, the nuanced human reality.
Just to mathematically guarantee that the remaining 58% is objectively, literally true.
Exactly.
You are trading recall for precision. You're giving the agent like anterograde amnesia for anything that isn't stated with robotic literalism.
And if we connect this to the bigger picture, it presents a really difficult architectural choice for systems engineers.
It definitely does.
You must decide whether the deployment requires an agent that occasionally hallucinates but captures the rich subtext of human interaction, or an agent that maintains a perfectly sterile database but remains entirely oblivious to implied context.
So what does this all mean for the listener, for the future of the agents we are interacting with? As we move toward delegating complex, long-term tasks to autonomous systems, whether they are managing our enterprise workflows or researching legal precedents or just coordinating our personal lives, the structural integrity of their memory stores will really define their utility.
Absolutely.
Because a single unchecked hallucination written to a vector database today becomes a toxic premise that corrupts the agent's logic for months. ConsistencyGate basically proves that post-hoc database filtering is a dead end.
Right. We must verify correctness at the point of extraction.
Exactly.
Practically speaking, this research dictates that we should confidently deploy these agents, utilizing that high-speed log prob shortcut on structured documents like code bases, medical logs, and financial filings.
Places where data is literal and bimodal.
Yes. However, we must remain highly skeptical of an agent's memory architecture when applied to open-ended human dialogue.
Because it just can't handle the subtext yet.
The verification mechanisms simply cannot yet balance factual strictness with the entropy of human speech without discarding massive amounts of valid data.
It fundamentally changes how we might have to speak to these agents to ensure they remember us correctly. We might have to start speaking in explicit, machine-readable, declarative sentences.
It's true. And this raises a final, broader question regarding the trajectory of personalized AI that I think is worth thinking about.
Okay.
If developers broadly implement strict extraction gates to mathematically eradicate hallucinations, we force the AI to systemically reject all implicit data.
Right.
By designing architectures that demand literal proof for every memory, are we inadvertently training our future AI companions to be obsessively literal?
That's a great point. If you message your agent saying, "It's pouring rain and my car won't start," a human understands the implicit reality that you are frustrated, you're going to be late, and you're likely stressed.
Exactly.
But a strictly gated AI might discard all of that emotional context because the word frustration wasn't explicitly quantified in the text string.
It just sees rain in a broken car.
Yeah. By enforcing a sterile database, we might be curing the hallucination problem, but actively killing the machine's ability to intuit.
It is an engineering trade-off that will fundamentally shape how these systems understand us in the future.
It really will. Well, thank you for joining us on this deep dive. Keep examining the architectures shaping your digital world, and we will see you next time.